We've been talking about precipitation reactions recently, and we've talked about how precipitation reactions generally involve ionic compounds. Now, when ionic compounds dissociate into solution, which is what they do when they're soluble, we like to talk about them in terms of their ions that are present. So we've talked about how sodium chloride, when it dissolves in water, it is dissolving into sodium ions and chloride ions. And that's what is present in the solution. So sometimes when we are writing out ionic equations and precipitation reactions, we like to be really explicit about what is present in the solution. And this allows us to show all of the soluble ionic compounds. When we do this, we do what's called a complete ionic equation. And this isn't really very different from what we would normally be writing. So imagine a regular equation here, where we have something like silver nitrate in solution, and we mix it with potassium iodide. Oops, that should be a plus. And then when these change partners, the silver iodide is a solid and the potassium nitrate stays dissolved. So when we talked about what this was really looking like, I said, well, look, the silver nitrate in the solution, we really have silver ions and we have nitrate ions, and they're all floating around together. And then in our potassium iodide solution, we really have potassium ions and iodide ions. And then when we put them together in a container, then the silver iodide hangs out as a solid, the precipitate, and then we also have potassium ions and nitrate ions floating around. So the complete ionic equation is basically just what I did, only without these little drawings of beakers. So we would write for silver nitrate in a complete ionic equation, we would write silver ion and nitrate ion. And you need to make sure that you write the charges in. It's an ionic equation, right? So we've got to have ions. And potassium iodide becomes potassium ion and iodide ion. And then this makes silver iodide, which is a solid, so it's not soluble, so we leave it stuck together. And then potassium and nitrate. And that's it. That's how you write a complete ionic equation. All of the soluble ionic compounds are written as dissociated ions. Specifically for ionic compounds. We could have molecular compounds in a reaction too, and we would not dissociate them. Insoluble ionic and any molecular compounds, we just leave them alone. So this is a complete ionic equation. And one of the things I want you to look at here is to look at what the active chemical species were here. Notice we have silver ion and iodide ion on one side of our arrow, and on the other side we have silver iodide, and that becomes a solid. So it's different on the left and the right. But notice that right here we have a nitrate, and over here we also just have a nitrate. It's not different. The same is true for the potassium and the potassium. These are just the same on both sides. So if you see some ions that are the same on both sides, we call these spectator ions. They just were hanging out. They look the same. On both sides of the arrow. So sometimes the spectator ions are kind of in the way, and we like to write a condensed version of the ionic equation that's called the Net Ionic Equation. So we take our complete ionic equation and we just remove the spectators. Now it's just the active components. So in this case, it would be silver ion plus iodide ion, making silver iodide. And that's all. That is a net ionic equation. So it's pretty straightforward. Writing the complete ionic equation can be a little bit cumbersome, but there's nothing particularly complicated about it. So let's go ahead and practice a couple more times to make sure we've got it. So let's see, our first practice problem, let's take some cobalt. I almost wrote antimony. That's not what we want. Let's do cobalt sulfate and barium chloride. And you know, while we're doing this, we can also have practice of writing in the phases and predicting the products. And for our second practice, let's do strontium sulfide and copper nitrate. So pause the video and practice with these two reactions. So the first thing that you are going to do is you are going to predict the products. The second thing you are going to do is you're going to balance if necessary. The third thing that you are going to do is write the complete ionic equation. The fourth thing you are going to do is identify the spectator ions, if there are any. And finally, you can write the net ionic equation. So pause the video and try these two out, and then we'll come back together and check your work. Welcome back. Let's do all these things. So if we check on our solubility table, most sulfates are soluble, including the cobalt, and most chlorides are soluble, including the barium. But barium sulfate is not soluble. So when these switch partners, then this one is going to be the precipitate. And if we look at our charges here, we know that sulfate is 2 minus, so that means the cobalt must be 2 plus. And we know that chloride is -1, and that means the barium is 2 plus. So that means that our cobalt chloride will finish this off. So we've done our first step. We predicted the products, and we can take a look at it and see that it's already balanced. So the next step is to write the complete ionic equation. Everything that is soluble should be separated into its component ions. So we have cobalt 2 plus, soluble, plus sulfate 2 minus, soluble, plus barium 2 plus, soluble. And now here, remember, this barium is hanging out with 2 chlorides. That's what this means. So that means we have 2 chloride ions. They don't stick together as Cl2 minus or 2,2 minus or anything like that. They separate as 2 individual chloride ions. So that's the left-hand side. Now on the right-hand side, we have barium sulfate, which is solid, so we don't separate it. It is not soluble. It does not dissociate. But the cobalt is, and it stays cobalt 2+, and the chlorides also just hang out. So we've written the complete ionic equation. Now we can identify the spectator ions because we can see the ones that don't change from the left to the right. So we can find that cobalt is hanging out as a soluble ion on both sides, and these two chlorides also are hanging out. So these are our spectator ions. And now finally we're ready to write the net ionic equation. So everything but the spectator ions would be barium plus sulfate makes barium sulfate. All right, so we finished with that first one. Let's take a look at the second one. As usual, these will both be soluble if this is a precipitation reaction on the left-hand side. And they are. We know that nitrates always are soluble, and sulfides are usually insoluble, but not with strontium. So that means that when we mix them together, the copper will precipitate with the sulfide. So when we look at this, we know that sulfide is -2 and strontium is +2. Nitrate is -1 and there's 2 of them. So that means copper is +2. So let's change those partners. Copper sulfide is a solid, and we're going to have strontium nitrate. And we can see it's already balanced. So we've already identified what our ions are and what our phases are. So now we can expand it into the complete ionic. So strontium ion and sulfide ion plus copper ion. And remember, we have 2 nitrates, so the 2 goes in front to make copper sulfide, leftover strontium ion, and leftover nitrate ions. So you're probably already starting to see which ones are spectator ions, the strontium in this case, and the nitrate. So our net ionic equation is copper plus sulfide makes copper sulfide. That's really all there is to writing net ionic equations and complete ionic equations. When we talk about some different kinds of reactions, we'll have some that are looking a little bit more complicated than this, but the principle is going to stay the same. So let's review that principle really quick here. For writing the complete ionic equation, if we have a soluble ionic compound, then we separate into ions. But be careful here, right? Here we had copper nitrate, and we separated this into copper ions and nitrate ions. So when you have an ion like this, you keep it together. This is part of the reason why we learn the polyatomic ions, because these guys travel as a unit. They don't separate into parts. Okay, they just stay as a nitrate ion unit. So you don't want to separate it into nitride and oxide or anything like that. Nope. You just leave it as this nitrate unit. So if we have soluble ionic compounds, then they separate into ions in solution. If they are insoluble ionic, then we just leave them as is. And if they are molecular, like maybe you have a reaction that has some hydrogen gas or something in it, we also leave those as they are. Okay, hopefully this clears up any questions you might have about total ionic or complete ionic equations and net ionic equations. And you should get some practice in our upcoming homework assignments and worksheets.